we will start now. I think we are online. I hope anyway soon we will be online. Okay. Good afternoon, everyone. We are pleased to see you in this European Membrane Society webinar for June 2024. It has become a tradition to meet almost all first Wednesday of the month. And today it's my pleasure to present Professor Murthy from the Maharajaya Saya Rao University of Baroda. Sorry for the mispronunciation. I think you better explain India. And who will give a nice, interesting presentation on the development of membrane for environmental protection. Now, Professor Murthy, I had the pleasure to meet last year in India as a PhD from ET Mumbai. Is clearly an impressive CV. I'm shortening a little bit just for giving you the space to speak. Since 2013, is fellow of the Gujarat Science Academy, and also held a fellowship and professorship internationally. His work experience spans both industry and academia, including roles at Johnson & Johnson, Head and Dean of the Faculty of Technology and Engineering. Is today the president of the Indian Membrane Society and holds several patents, a lot of paper published, around 60, led various research projects, contributing significantly in the membrane field. So I will leave you the space. We are really pleased to have you presenting this webinar.
Thank you, Professor Elena Tachi. It was a great pleasure to meet you last year at our city of Baroda, at the Maharaja Sayajirao University of Baroda. And thank you for this invitation. And it's just a coincidence that we are meeting on a International Environmental Day, and it happens that 5th of June with a theme on land restoration, desertification, and drought resilience. And especially for people who come from India, drought means that there is no rains for that particular year or maybe for a few years. And that's where the water comes in. And so the resilience of drought should be, we should be able to overcome using technology. That's what I feel. And so I just go about the presentation based on some of the work we do on the membranes, try to develop some new membranes, and for environmental protection, basically remediation, and look at how we can improve the efficiency of the membranes. But before I go into the main theme of the work, this is what is the UN Sustainable Goals, the 17 Sustainable Goals, and among them, the sixth one, which is 86, which talks about clean water and sanitation. And when we talk of clean water, it is again potable water, drinking water, and sanitation, which is essentially wastewater treatment. So these two processes both require the membranes and the development of newer membrane materials so that we have better efficiencies of these membranes. But if you go back to the almost 60 years back, one of the first patent on the membranes was by Professor Sidney Loeb and Saurirajan, essentially talking of high flow porous membranes for separating water from saline solutions. So maybe drought remediation, resilience should come from such kind of a technologies. And this essentially was by two, that is Professor Sidney Loeb and Srinivas Saurirajan. What do they say? They talk about making clean water from seawater. And one of the very recent reports, which was in 2023, I have taken this report, it talks about the way the development of the membranes is taking place. These are essentially the desalination plants across the world. And of course, because we all use our screens, I don't know whether we'll be able to see the details of what is written, but I would like to focus on the water cost, which comes to around USD 0.73 per metric cube of water, which is even as of today is quite high. And some of the treatment plants which are there essentially use the MSF multi-stage flush or the RO technology, almost producing 1000 mLDs per day. And as compared to these two, which are both situated in Saudi Arabia, the one which is in India itself is almost 10 times less. Even though we are heading towards one of the bigger economies of the world, I think there is a huge scope for the desalination, not thermal desalination. Of course, thermal desalination has been there, but then because of the energy cost, I think the membrane-based desalination or the RO technology would be a solution or a move forward to look at the water requirements of the whole of the population of almost 1.4 billion. And as of the reports which is coming up, there is scope for the reducing the desalination cost to less than zero point 0.4 per meter cube. And also, when we talk of desalination, what is required is the water quality parameters that need particular consideration in desalinated water include bromide, potassium, sodium, boron. Actually, boron is one of the very toxic element, and it's harmful to plant health and to human health also, which and the WHO, the World Health Organization, it gives about 2.4 as the limit for the RO, a limit for the element in water, and it is achievable by RO technologies. Again, these data are from the groundwater intelligence of Desal data last year. But let's go back a bit basic. What is wastewater? It is defined as spent water. Some of the sources of these the sources are domestic wastewater, which contains vegetable matter, grease, scum, detergents, etc. The industrial wastewater, which contains toxic chemicals, metals, very strong organics. The brackish water, again, between 1000 to 10,000 ppm of the TDS, and the seawater, again, which is having 35,000 ppm of the dissolved solids. And as of 2017, of course, we are almost now 6-7 years away from this report. Over 80% of the world's wastewater and over 95% in some least developed countries is released to environment without treatment. And that's where the environment comes in, and that's where the membranes have a crucial role to play in not only separating some of the high-tech applications, but as basic as water treatment and trying to remediate the water which has already been used in many of the applications. But desalination, essentially, very briefly, I will go to desalination. What I would like to focus that desalination happens only through a semi-permeable membrane. And this semi-permeable membrane essentially tries to move water through the membrane. That means essentially looking at water flowing through the membrane. That's what is essential. What is reject is essentially what is left behind after the treatment. But what is this semi-permeable membrane? Now, if you go back to the basics of the physical chemistry or chemical engineering part of it, the Gibbs adsorption equation essentially talks about the surface excess of a solute and a dissolved solid in a solvent with gamma as sigma as the surface tension. Now, if you look at the surface tension change with concentration of sodium chloride, the seawater concentration 3.5, essentially there is a curve which talks about what is the surface tension. Surface tension increases with the concentration of the NaCl or in, the electrolyte in the water, pure water. Now, when you look at the Gibbs absorption and the surface excess, one can calculate what is the interfacial water thickness as compared to the concentration of the NaCl. Some of this very basic thing is that there is a layer on the water at the interface between the water liquid and the gas or a solid, which essentially consists of pure water. So if I take A as the salt water, then there is a thickness which is in the angstroms range. Here it shows as almost 4 angstroms, which is represented by the blue ball. Now, this is what is the clean water or the pure water. This is very interesting actually. And if we are able to skim this pure water, then that pure water layer is again replaced by, from the seawater, the pure water, which means that if you are able to continuously skim the ocean or the sea, we should be able to get enough quantities of clean water. So that's where the technology plays a huge role in how do we do this activity of desalination or getting clean water from a salt solution, which is roughly about 3.5% weight percent, which is not much actually. But then, what are the limitations of this? How can we do this clean water skimming from the seawater? Now, if you look at the membrane surface, as I mentioned, there is a layer of almost 4 angstroms, which means that if we have a pore which is twice the thickness of that, that means roughly in the range of 1 nanometer, then that pore would take out the clean water and retain whatever the salts are there. So you have this membrane scheme, which is here, the bulk solution phase, which is consisting of essentially the salt solution, and we have an interfacial region and a film surface of appropriate chemical nature. That's where it's very important. And we have a critical pore diameter. And this critical pore diameter essentially is the 1 angstrom range. And it has been shown by many that it is the preferential sorption capillary flow mechanism which leads to the desalination process. Now, if you have this demineralized water at the surface and you have a porous film, then the critical pore diameter of the on the film surface or the interface should be twice the thickness of that clean water layer. So the essential components of any membrane separation process would be an interface, a morphology of the film or the membrane, and the transport which happens through that pore, which is essentially of the dimensions of 1 nanometer. Now, how do we get the dimensions of 1 nanometer? Now, just to give a highlight again of what is the market, the global membrane separation market is expected to grow at compounded rate of 10% from 13 to 19. Again, this data is just given in 2015, which is almost now 10-year-old. But then I think that something different is happening. The mining of the market of mining water again is expected to grow by 85% by 2019, and this was predicted by Professor Enrico Rioli in one of his presentations to when he was here in Baroda at the MS University of Baroda. So this is with this background. How do we look at the membrane development which has happened since the last 60 years? One of the earliest conventional membranes of cellulose esters was essentially a hydrophobic membrane, but then there were fouling issues which came up, and so the thin film composite membranes were devised. That was in 1978. And then, because of the separation of the thin film composite membrane, because essentially it was a separate polymer layer on a membrane, the addition between the membrane film and the base polymer was an issue. The salt water was an issue, the chlorine was an issue. And so, to overcome all this, the mixed matrix membranes were devised. But essentially, what we at this stage know that there are no mixed matrix membranes commercially available. Most of the market now is filled with TFCs and not any of these mixed matrix membranes. One of the reasons for this mixed matrix membrane still not been able to be commercially available is the variation or the lack of understanding of this mixed matrix membrane. And it was this issue which made us to think, why is it that we are not able to have commercially available mixed matrix membranes? And we have to look at the science of it. And we thought that since in a conventional membrane, the huge pressures which are applied on the membrane, roughly up to 50 bar, that leads to compaction, the fouling, the closure of the pores, and all that. Right? And so, if we are able to overcome all these issues of the membranes, then maybe we should be able to have much better commercial membranes of mixed matrix. But then, why should mixed matrix membranes or the composite membranes are the future? A cartoon which was again in 2015, which says that in a typical auto configuration, which is a single stage, the energy efficiency is very poor, and but then it is highly practical. Anyone can do auto, just have a small plant, and then you can go for auto, but it is not energy efficient. But when you go for a multi-stage pass, then it is energy efficient, but it's not practical. It requires huge areas of land. And similarly, if you have a multi-stage closed circuit system, then it could be both energy efficient but practical. But then the issue is that how many number of the multi-stage can be done. Now, seawater can be circulated only twice before the osmotic pressure of the feed exceeds the sustainable pressure of the membrane. So, if one has a concentrated salt solution, then the osmotic pressures are much higher, more than 50 bars maybe, and so the membrane material itself cannot withstand such kind of a pressures, and there are problems in that. So there is urgent need to come up with membranes which are robust and can do the desalination process much more easier than what it is being done now. And there is a need to reduce the energy cost from roughly up to 3.5 kilowatt per hour to 1.5 kilowatt per hour. And so the solution could be that there was a report in 2004, 2003, that water flows through the nanotubes. So, if water can flow through a nanotube, and if you are able to align these nanotubes inside a matrix, a membrane matrix, then water does flow through these membranes, through these nanotubes in a single file, just like ants walk in a single file. Similarly, because of the polarity difference between the H and O, the water molecules go through, as has been shown on the top right corner, the water molecules in a single file can flow through these carbon nanotubes tubes, whether it is single walled or double walled or multi walled. But what is the proof for that? Actually, there is again a report based on a study and which came up in 2006, which says that comparing the water flow through a CNT membrane, through CNTs, and through a membrane pore, typical polycarbonate pore, then if you have to look at the pressure difference or the pressure enhancement, then in case of double walled carbon nanotubes, this is a study reported, it shows that the slip lengths for the flow of water through these carbon nanotubes, double walled, is much higher. It's almost 500 times higher, or even 200 times higher, and the large value of these slip lengths is indicative of the nearly frictionless flow of water through these nanotubes. So the idea is, can we force the water to flow through the carbon nanotubes once it is dispersed into a polymer matrix? And that was the idea where we started working on. It would functionalize carbon nanotube, of course, dispersed in a polymer matrix, should improve the interaction between the polymer and the carbon nanotubes. It could control the pores and channels and should be able to facilitate the frictionless transport of water through these pores or channels. So this is typical of mimicking what is called a biological cell membrane. If you look at the cell membranes which we all have, these are lipid bilayers actually, right? They are hydrophobic, but then they are made up or they are encapsulated around these aquaporins are encapsulated, which transport, selective transport of the or exchange of sodium and potassium through this, and water transport is done. So this is what I would like to say is that a biological cell membrane essentially is a mixed matrix membrane, the matrix being the hydrophobic bilipid layer, and you have the aquaporin molecule, which again has a hydrophobic exterior and a hydrophilic interior. So this is how one can play with the mixed matrix membrane if you are able to design membranes which are having CNTs and have functionalities which are open onto the membrane surface. So if you look at the porous structure of a membrane, a typical membrane, then it would have different types of pores: blind pore, through pore, or isolated pore, which is the cross section of the membrane thickness. But then if you are able to incorporate these CNTs and align them, how do we align them? The technologies are, there are reports where alignment is possible, and then it's possible that water can flow through these membranes. If water can flow through these membranes, then you'd have higher fluxes. The membrane is much more robust because of the presence of the CNTs inside the matrix. It can withstand much higher pressures, and that's what we have found in many of the studies which we have done. Just to look at not only CNTs but also on the graphene oxides. Of course, I just wanted to highlight that the presence of graphene oxide also has, as a mixed matrix membrane, has applications in carbon dioxide capture. Again, one of the environmental remediation issues which are there. And if we are able to do that, then we should be able to have much better membrane characteristics. So we did some studies on this, just to highlight that many of these membranes were made by a phase inversion process, where we have a functionalized CNTs inside either it's a polysulfone or a polysulfone. And when we look at the pore diameters of the membranes when they were having the CNTs and without the CNTs, when there were no CNTs, then we had a smallest pore diameter with a contact angle of 77 and a pore diameter of 100 nanometers. But when you're able to incorporate carbon nanotubes, then you could reduce the membrane pore diameter to roughly about 25 nanometers and a contact angle of about 26. So there is a reduction in the contact angle also, because these, even though the CNTs are hydrophobic on the surface, the functionalization of these CNTs tends to put the functionalities onto the surface. The issue is here that we are not functionalizing the membrane either which is polysulfone or polyether sulfone, but what we are trying to do is functionalize the CNT. If you are able to functionalize the CNT and use a functional CNT onto the membrane surface, then we are trying to create different surface characteristics on the membrane. And we did some studies on that, permeation studies, and what we found that we had high permeate flows with very low, actually, permeate flow was as low as the pressure was essentially about 5 bar, and which is typically 10 times less than what you find in a RO. And also the flux, the stability of the flux is very important. We're able to get stable fluxes. One of the problems with this TFCs is the change in the flux with time. Actually, as the time increases, because of the high pressures, the fluxes of these TFC membranes reduces. That's where you have to reduce the module, and other cleaning processes have to be undergone. But essentially, that is what adds to the cost of a membrane process. To look at the membrane morphology, a classical porous media would have, of course, I have shown it as a cartoon which shows spherical, but actually they are finger-like. But then these finger-like are much wider than what you see when you have the CNTs incorporated into the membranes. And when we are talking of the membranes, then we have to look at consider the length of the nanotubes in the composite membranes also is very important. And when we try to look at the pore structure of this, now we wanted to use a different technique than the mercury porometer or typical capillary flow. What we wanted to see is if we can have no pressure on the membrane and still be able to find out what kind of a pore structure is having, then we have to use a non-destructive method like small angle neutron scattering. Now, the D2O is a very good scatterer, and since we are able to have, if you can soak these membranes into ordinary DI water, deionized water, and compare it with the membrane soaked in heavy water, which is D2O, what we see is that the pore radiuses, essentially what we are detecting is from 14, or for example, M41, which is essentially a functionalized membrane, then CNT membrane, the pore radius reduces almost already, or we can detect smaller pores actually, now, which is 7.4, whereas in the other case it is 13.5. Now, but then when we look at the correlation length, the correlation length essentially talks of how separated these CNTs or the pores are inside the matrix. Now, what we observed is that the correlation length remains the same even though the pore radiuses are being detected smaller. So what we found is that if a large pore is there, then the number of pores is much less than as compared to a small pore, which means that we are essentially talking of the density of the pores. Small pore size, higher density, and so the correlation length remains the same whether we are seeing smaller pores or we are as against to when we are seeing the bigger pores. And of course, when we look at the contact angles, we are getting very low contact angles, as low as, of course, it can go to much less than 60 also. We are seeing much lesser. And then compared to that, when we look at the pure water flux, we get much higher fluxes as compared to when we have a pore radius. So the pore radius now is not controlling the flux. The flux is much better when we have a smaller pore as compared to a bigger pore. And so once we have a functionalized CNT, one should be able to do good chemistry on these functionalization for functionalized CNTs. Like for example, what we did was you take azide terminal CNT and one can do a simple click reaction where we create a triazole ring on the surface. And how do we know that this click reaction has resulted in a surface which is having triazole rings? The best way is to see whether the azide group which is there has converted to a triazole. So that we can find out by the XPS method. And when we found that, a non-click reaction membrane surface which has the azide groups on the surface, it shows two separate peaks. And when we do the click reaction, what we found is that two peaks resolve into one single peak, and this resolution of this peak can be explained very easily from the structure of the azide group. Actually, the azide group has 3 nitrogens, and these 3 nitrogens, when there is no triazole on the nitrogen, then there are 2 separate nitrogen charges on the azide, and that's the reason why we have 2 separate peaks which is observed. But the moment we convert them into a triazole, all these 3 nitrogens, because of the resonance effect, are uniform or equally charged, and so these 2 peaks then resolve into a single peak. So that was one of the very good confirmation that our click reaction has taken place on the membrane surface. Now, the moment we have this kind of a click reaction on the membrane surface, we are getting 3 nitrogens which can have different properties depending on the pH. How do we do that? We do the zeta potential studies. Okay, before that, what we did was we did the membrane performance, and we could get separation characteristics as high as 93. Of course, we got much higher. And then what happens is that the flux recovery ratio also improves the moment we do the click reaction on the membrane surface. The flux recovery ratio is as high as 92. That means that we can back flush the membrane to remove if any fouling is there. That means that the membrane surface is fouling resistant actually. That's what we found from these studies of the membranes. And when you look at the surface characteristics, that means that's how we can see what is the surface characteristics of this membrane. And what we found is that if you change the pH, one can change the surface characteristics of the zeta potential surface. And what we can see is the red line. If you see that at one pH it is positive, at the other pH one gets a negative surface characteristics, which means that we can now play with the feed which has a different characteristics and the membrane behaves differently. Now, this kind of a study we found in one of the science advances study. I'll just go to that. But this is the summary of what we get is we get very low contact angles using this kind of a surface modification of the membrane. And of course, we did the morphology studies by AFM, smoother surface. If you use multi-wall carbon nanotubes or oxidized single-wall carbon nanotubes, we have different characteristics because of the multi-wall has higher functionalities on the surface, and so we get a much better characteristics of this membrane. And we did some studies on binary mixtures also. So one can have a selectivity of the metal ions which are being removed, whether it is lead or copper or some other metal also. One can have selective separation of whether it is copper or lead based on how we change the membrane surface. Of course, these are studies of the other salts which I have used, and also the surface now becomes much more conductive. And what we have seen is that this membrane surface, also because of the charged nature of the membrane surface, we have conductivities which are much better. Something similar, some of the charged membranes. And recently, as I mentioned, this is just wanted to highlight that this kind of a Janus membrane, that means that one can change the membrane surface both on two sides. Now, as of now, what we have studied is on one side of the membrane only. But then there are membranes now which are just recently published in Science Advances, which has both the sides. It can change the characteristics based on what kind of charges are there. So, which has switchable affinities. So, you can have electrostatic interactions or hydrophobic interactions based on the charge on that particular membrane surface. So, the membrane characteristic essentially is to do with the surface of the membrane. And so, since it was a surface phenomenon, we try to do some other chemistry on the membrane surfaces using the functionalities which we have introduced onto the CNTs. So we did some reactions with cyanuric chloride, then trimethyl chloride, all of them changing the functionality on the membrane surface. This is just a cartoon. The thick block, of course, it is much thinner, but to show the comparison between the CNTs, which are essentially in the micron dimensions in terms of length and nanometer dimensions in terms of the diameter, we showed that this membrane thickness, the CNTs, are aligned perpendicular to the membrane surface. Now, the question is, how are we able to align? What is the proof for that? The proof, one thing is that the membrane surface is charged now. If you take polysulfone or polyether sulfone and we incorporate the functionalized CNTs, there is charges on the surface. We have found it by surface studies, zeta potential studies, as well as from the XPS studies, that we are seeing charges on the surface. So we are able to play by using simple chemistry with the charge on the surface. We can have different characteristics. Again, we can have anti-fouling studies. The FRR is quite high, 96, and the irreversible fouling is much less, depending on how much percentage of. So one can use polyether sulfone or polysulfone. Here it is polyether sulfone. Also, some studies we are able to go up to separation of 99.2% of copper or 97% chromium of the rejection of these membranes. One more surface modification, again, we try to do is on using branched polyethylene. Again, we are introducing nitrogen groups with spacers. One can change the spacer length. So we should be able to change the surface characteristics of the membranes. Many of these results are with the last two slides are under review, and we hope that this kind of a studies would push forward the mixed matrix membranes and the charged membranes surface, so that we can have selective separation, whether it is heavy metals or we have a selective, if it is wastewater desalination, wastewater. So we can also have such kind of a membrane because the fouling is less than. When we talk of wastewater treatment, then fouling is a major issue there. Now, if we have such kind of membranes, then fouling would be reduced, and we have much better fluxes when we talk of the membrane-based separation. So I think this is one of the last slides. Again, we have very good separations. We also started working on since we had good success with the CNTs, we want to look at the functionalized graphene oxide also. Of course, we are still in the initial stages, but we feel that since there are reports of carbon dioxide capture using these uh, functionalized reduced graphene oxide membranes, we are looking in the direction whether these same membranes can be used for carbon dioxide capture for environmental remediation. And what we find is this rejection again for heavy metals, the rejections are much better. I mean, these are initial studies of the reduced graphene oxide, and we are sure that we should be able to get much better rejections using functionalized reduced graphene oxide. And this is some of the work which we are doing in our group. And I think I'm almost done. This is my last slide. And I would like to acknowledge some of my students who have been working with me for the past 10, 15 years, and some of the funding which has come from Government of India, the Grants Commission, the Department of Atomic Energy, and of course from industry who have been supporting me. And then we are collaborating with one industry on using these membranes for various applications. I thank you all for patiently listening, and I hope that this presentation has uh, given a broad idea of the kind of work which we are doing in terms of the mixed matrix membranes. Thank you all.
Thank you, Professor Murthy. Okay, you can leave also the last, I think, the last page with okay, the beauty of your city, because I really appreciate it. Thank you for the presentation. We have just some delay between the YouTube presentation, so maybe some question will appear later. In the
Sure.
meantime, I think it's also useful to thank you for your presentation. It's quite useful, and I would like to ask you, make some question. First of all, you were speaking about how to reduce the fouling. So do you think that anyway the way you are proceeding is the best way, and you would like also to continue to solve this problem, or you think that in the meantime you are also finding other solution, uh, considering anyway CNT structure inserted in your membranes?
Yes. Yes. So yeah, I mean, we are using a flat sheet membranes. Basically, we are not going for uh, some other membranes, but we are looking at flat sheet membranes and trying to align the carbon nanotubes, right? And when we talk of aligning these onto the membrane surface with the mouth open on the membrane surface is a challenge. Of course, we are getting what is called indications through the membrane surface, right? But we are not still not been able to take a TEM of a membrane yet. So we are trying to look at a TEM of a membrane where we can see at least the CNTs in a matrix. So that is one area where I think that uh, we have a lot of challenges. The second part is that the robustness of the membrane is very high. We did some, of course, I didn't show it here. The TGA of these membranes is quite high. They are quite stable, and of course, mechanically quite stable. Did I answer that, or is it that's what?
Yes, yes. Anyway, it's quite challenging, I think, to have CNT inserted in the correct way. I think it's one of
Yes.
the yes. And
Yeah.
what about also GO, graphene oxide? Do you face
Yes.
other challenges, or which is the main, I'll say, shortcoming of
See,
this material?
what I believe is the method of casting the membrane. What we are using is the phase inversion technique, right? And when we dip the cast sheet into a polar medium, right? So it is that which helps in the functional groups onto the membrane surface. and not into the bulk. So if it is RGO, functionalized graphene oxide, again, the functionalities of on the graphene oxide are the ones which would turn towards the hydrophilic side of water. Normally, these are we when we talk of the phase inversion process, we are essentially a non-polar matrix. We are dipping it into a polar like water. Of course, it has pore formers and all that. But then that is where the interaction takes place between the membrane dope solution and the water. And that's where the alignment should happen in a chemical way. So, yeah, of course. I mean, we still have not been able to observe a CNT inside a membrane, which is aligned.
And I have also another question. It changed a lot if you consider the single or multi-walled carbon
We did work
nanotubes.
on
I
both.
think.
We did work on both, but since single walls are still expensive, so we focus more on multi wall.
Okay, because it's easier, so could be practical also to
Yeah.
this solution. Yes.
One more thing is that why single wall is not a good. What we felt was when we do the functionalization could happen on the CNT surface, single wall CNT surface also, and so the structure of the CNT would get damaged.
Mm,
Whereas in case of a multi-walled, even if you have the surface getting functionalized, the inner walls still retain their tubular structure.
mm.
So that's how we are focusing on only on multi-walled and not on single-walled.
Yes, it's practical essentially in this sense,
Yeah.
clearly.
Yes.
Clearly. And do you have also idea to work on graphene, or you think that CNT can are much better in comparison to the capability of?
My personal would be the CNTs because it follows the tube, a pore, a channel which is helping in taking water into the through it,
Mm.
right? Yeah, so my basic attempt is to force water through the CNTs.
Okay. And between layers of graphene could be depends on the interlayer spacing. So at the end,
Exactly.
is much more difficult to control
Much more
instead
difficult
just
to,
nanotube.
yes,
Okay.
yes.
On the other side, maybe layering graphene is simpler than just aligning carbon nanotubes. So in
Yeah,
that case,
yes,
different
yes.
challenges has to be.
A graphene is a sheet again.
Yes.
It's not a tube.
Mm,
So I believe that of course if it's a graphene sheet, now the sheet could be either perpendicular to the membrane surface or it could be parallel to the membrane surface, or there could be many multi layers on the membrane inside the bulk of the membrane. There are challenges. We still don't understand much of the graphene oxide. Of course, there are reports which say that you have channels which are happening inside the membrane. Good journals have this membrane, this graphene oxide based membranes, mixed matrix membranes.
okay. Generally, we have anyway some comments. Few. Maybe this delayed. We are almost on time, so I think I would like to thank you very much. Also, maybe I can make another question. Is about if you can just give. I'll say some information about also the society. European Membrane Society clearly behaves
Yes,
to the World Association of Society, and also Indian is in
right.
this area. So I think maybe you can also give us some information about the society and also the possibility that how which is the how to say the scope of the society. Give just some information on this. Maybe it's also interesting for our for the people listening the webinar. This could be also okay if you can.
Yes, yes, yes. So actually, we would like to very much interact with the membrane community. We did interact with, I mean, with the ASEAN membrane societies, and I think this is one of the. I mean, after a long time, I think we as EMS and RMS we are interacting. We could look at some joint projects, some collaborative interactions, like uh, applying for some of these funding agencies for joint work, and trying to strengthen our capabilities.
Okay, so thank you very much. We have also Indian students and professor between our members, and we are really
Mhm.
happy also to have this international membership.
Yes.
And I hope that also people from EMS will join also your society, also to increase the, how to say.
Yes.
And
Yes.
with this, I would like to thank you. I know that it's also late now. I think it's about 9 in the evening, I
Yeah, it's
suppose.
it's about 8:20 here in India.
8:20 here. So
Yeah.
thank you very much for attending, and I'm sure that when you will go also on YouTube, you will see that several visualization then appear, because all these seminar webinar that we are doing are quite general and are really interesting, not only for the, how to say, the
Yes.
members, the general members, but also for also students that can start following and learning a little bit from membranes directly from the people. And okay, with this, thank you very much, Professor Murthy.
Thank
And
you.
I would like to thank also all the participants, and meeting you again in the July webinar that is foreseen for the 3rd of July. Thank you.
Okay.
Thank you,
So
everybody.
thank you. Thank you very much.
Bye-bye.
Thank you very much.
Bye-bye.